Hello. So, welcome back to the stereochemistry discussion. Last two lectures we have talked about the isomerism, the structure, mainly the structural isomerism, and the representation of 3D structures in two-dimensional plane, different notations, different projection formulas we have discussed. This Newman, Sohos, Wedge, and Fisher projections. And if we want to study the optical isomerism, all those structures should be very thorough, because this optical isomerism is the isomerism which results the difference in orientation of the groups around a central atom. To understand, so if you want to understand the isomers, this all this formulas, all these projection formulas should be very thorough. So you should rewind, means just recall all those things. And in this lecture, we will be also studying some new terms, that is chirality, enantiomers, diastereomers, and we'll look into the examples of each class. So shall we go to this
Optical isomerism.
These all things, as I told, whether it is Newman, Sohos, Wedge, or Fisher representation, this we could be able to identify the corresponding isomers. Before going to optical isomerism, first we should be understand the term chirality. Chirality means handedness. Handedness means we have two hands, no? This right hand and left hand. Both are almost similar. If we take it independently, we
both are
say
similar.
they are similar. We have 5 fingers, and almost all fingers are looking same. So all fingers on the both hands, means thumb, index, all in the two hands are looking same. So the question is that whether are they identical?
Yeah, I felt it's almost identical.
It is not so, because if when we call an object as identical, is that they it that object and its mirror image should be exactly looks like similar. And when if we keep the mirror image and the object on one over the other, they will be perfectly matching or
Okay. In case
so
of these hands, what is happening is our left hand is a mirror image of our right hand.
yeah
So both are mirror images to each other.
yeah
If we are keeping a mirror here, it is like that only.
it will feel
But
like that only,
whenever we are keeping the left hand on top of the right hand, it will not exactly match each other.
it won't superimpose.
Okay.
It will be like
The word is superimposable.
it is.
So both the hands are non-superimposable to
It will
each
come
other.
like this. Okay.
Okay. So this is not a chemical property, madam, isn't it?
It is a material property. We can observe this phenomenon all means around us.
Yeah.
Some will be chiral, some will be achiral. We can see the chair you are sitting.
Yes.
So that will be a chiral object.
That we can keep
The
on
mirror
and
images
mirror image
are
of that chair we can keep on this thing.
the
We can go with this specs example itself, madam. One specs, if you are taking a mirror image of that specs, that is exactly superimposable to each other.
Yes.
And whenever the specs one side is colored and other side is transparent, then we are taking the mirror image, then that will not be able to superimpose to each other even after rotating that left and right or 180-degree, or then also it will never become superimposable to each other. Such objects are named as chiral objects.
Chiral objects, and the chiral objects will always be non-superimposable, because in this case the mirror image of that specs will be that blue portion will be coming at the left side, and if we keep that mirror image on the exact structure, that white and blue will be coming one over the other. So that is not a superimposable images things.
Okay.
So
chirality.
This can observe everywhere. We can just take the example of alphabets.
Yeah.
Some are superimposable, some are non-superimposable. We can just look at the letter A. We can have the mirror image is of A like that, and if we keep that mirror image on the structure, we will that can be exactly one over the other. Similarly, it is the case with letter M and it's the case with letter O. But if you take that letter R, the mirror image will come like
it is not at all possible to this reverse R is not
so
possible
if we
to
keep that
superimpose here.
on other, then
J, F,
J
everything
also.
is like that.
Yeah.
What then I have a doubt that what makes this molecule achiral, what makes this object achiral and what makes it chiral? What may be the reason, madam?
It is the symmetry present in the molecule. Symmetry
means
if we have there are several symmetry elements, and if we have any of the symmetry elements, I will say some, that is, if a plane of symmetry, plane is a symmetry element, a point is a symmetry element, and if center of symmetry, point means a center of symmetry. So if we have a plane and if we keep a plane at one point, we can have the two halves are similar. The one either side of that plane will be looking same.
Yeah.
Okay,
That
so
means
in case of M, you can put a plane on this direction, no? So that two halves will be similar. And in the same with the letter A also.
Yeah.
You can cut that molecule in like that, and the two halves will be exactly similar. In case of O, we can have many planes. Actually, so many planes are there. So we can get the equal halves on either side. But in the case of letter R, J, and F, we can't get a plane anywhere. Or any symmetry element is not there. You can't get a center of symmetry or anything is there. So that object is not having any symmetry and they are chiral objects, and the objects which have a symmetry element in that, they will be achiral objects.
Okay, madam. Now it is very clear to me. Whenever a material that is having that we are having a symmetry. Symmetry means here we are able to cut A into two equal halves.
Yes.
There is through center we are cutting it. We can make into two equal halves. That kind of objects we can call as achiral, because there it will become this mirror image also, it will become superimposable to it. And in case of O, if you see, we can cut it into two cutting we can do. So four halves will be equal only.
Yes.
So like that also we can say, isn't it, madam?
Yes.
Yeah. So in case of a this is all 2D examples. If you go to a 3D example, that is a specs. A specs also, if you are cutting like this, then this is having two equal halves. Both the halves look similar only. So there also it behaves as a chiral. Okay. In case of chair also, we can cut the chair exactly equal into two halves. Desk, bench, everything we can cut into two exactly equal halves. So that will be achiral objects.
Okay.
So that will make that whatever the achiral objects that is having equal cutting is possible, that will make a superimposable mirror image only. Whichever making, or we are not able to cut into two equal halves, then that object will behave as a chiral object. So we are now onwards, we are going to focus more about chiral object.
Yes, because
where the symmetry is very less.
Just got the examples of some materials. So this is applicable to the chemical world also. So what these molecules we are composed of, we have molecules, no, atoms and molecules. So all these things are, some will be chiral, some will be achiral. So we will look into that, and what is the importance of this chirality, that also we can discuss now. So this is alanine, no?
Right. Yeah, this is a alanine molecule.
So this have all the atoms attached to the central carbon is different. So this carbon is said to be asymmetric carbon. Okay, if the substituents on the carbon atoms are different, or normally we have four substituents, and if all these four are different, they are said to be asymmetric carbon.
For a sp3 carbon, where the four units are of different type, then we can name that carbon as an asymmetric carbon. Isn't it, madam?
Yes, asymmetric carbon or
and
chiral
this
carbon.
this carbon will always form a no this carbon and this molecule with asymmetric center will always form a non-superimposable mirror image. So that kind of isomers, or that kind of pair is called as enantiomers or optical isomers.
So because why we call as optical isomers is that when we pass light through this molecule, they will rotate the molecule, plane polarized light, to a particular direction. That is what optical act.
Whenever an asymmetric carbon is present in a molecule, that molecule will become optically active.
Yes.
Or that is a particular condition also is there. Whenever a molecule that is having an asymmetric center and that is not having any symmetry point in it, then that molecule definitely will show an optical activity. Optical activity, we can simply speak like this. Whenever a light is having, usually we can see the light will be like, it will be having many directions.
Yeah, it can propagate in all directions.
All directions. Whenever light is coming from its source, it will be moving through different directions. Whenever this is moving through a polarization filter,
we are restricting that
or other will be
direction.
Only one direction light it will go through. Such light is coming through this portion, and this is having a direction like this. Whenever it is passing through a D-glucose medium or any optical isomer sample medium, then it will, in case of, if it is D-glucose, it will rotate the plane polarized light to right, and if it is something L-LEVOS system, then it will rotate to left.
Or it will have a plus direction and minus direction.
Yeah, that we can notate plus direction or minus rotation. So basically, if you see, this is a polarimeter. This is very cheap. It is cheap equipment only. It is not that costly equipment. So if light is passing through the polarimeter, we will be able to see how which side light is rotating and all.
Yeah, if we have a sample in that C portion, if we have a sample which is optically inactive molecule, then we will get that light in a straight way, no?
Yeah, as such only.
As such, yeah. So those molecules which are optically active only will exhibit this phenomena that it can rotate that light to a particular direction. If that direction means either in the positive way or in a negative angle.
Positive or negative means that is right. Basically, right or left you will see in the instrument. We will be looking through this portion.
Yeah. So this optically active molecule only exhibit this phenomena. As what is the criterion for optical activity is that those molecules should be chiral, and this chirality in turn is as a result of this asymmetry, no?
Yeah.
4 different groups around this carbon center.
That we can go a little bit deep, madam.
Yes. So the minimum condition for optical activity or this chirality is that the molecule should be asymmetric. And this asymmetric means it does not have any elements of symmetry, either prime axis or center of symmetry or alternating axis of symmetry, anything.
I don't think that equally cutting is
impossible. Yeah, by taking any of these elements of symmetry, if we are not getting equal halves, then they are called as symmetric.
So, for an optical isomer, there's chiral center, and that chiral center means that there will be an asymmetric carbon in it. Asymmetric carbon means a carbon that is attached to 4 different functional groups or 4 different groups it is attached. Then we can name that carbon as an asymmetric carbon or asymmetric center. Like that we will be naming it. And there is optical isomers or enantiomers. Simply we are naming these optical isomers as enantiomers. That enantiomers have the ability to rotate the plane polarized lights, and that plane polarized light rotation may be either right or to left. If it is a right, if the molecule rotates the plane polarized light to right, then we can name that compound as a dextrorotatory or plus form, or we are simply naming it as D.
Dextrorotatory, and if it is rotating to left, it is called as levorotatory. And this enantiomers means those objects which are having non-superimposable mirror image. So, if the original object rotate the light to the plus direction, then its mirror image will be rotating the light to minus direction, opposite.
Yeah.
So that's clear, no?
Yeah, very clear. So, what, as we said, for an optical isomer, there should be a chiral center. So here in 1-chlorobutane, there is no chiral center is present. All carbon here, this carbon will not behave because all hydrogens are repeating, and this is also two hydrogen. Yeah. So this is a this is a chiral.
So whereas in 2-chlorobutane, the green carbon is chiral because all the four groups are different.
This carbon. This is one is at one group is hydrogen, then one is chlorine, one is CH3, and one is ethane. So there is a asymmetric center present in it. So this can have a optical isomer or enantiomer. This can exhibit either in the form of plus 2-chlorobutane or minus 2-chlorobutane or dextro 2-chlorobutane or 2-chlorobutane. Remaining all are not having any chiral center. So this will be optic. These all these three will be optically inactive, and where this will be optically active.
At least one carbon should be, if in a molecule, if there are many carbon atoms, for a molecule to, and that molecule to be optically active, at least one of the carbon atoms should be asymmetric or it should be chiral. Okay. Then only that whole molecule can be optically active.
Okay.
These are some examples. First one is the D-glucose. We will have the D-glucose and L-glucose. The D-glucose means the maximum numbered asymmetric carbon, that is the fifth carbon. This have the OH on the right, this D-glucose, and OH on the left, it is the L-glucose.
So naming will be like that. Yeah. So the highest carbon, from here we will start naming 1, 2, 3, 4, 5, 6. So second, third, fourth, and fifth carbons are asymmetric center only. So we are highest carbon we are taking, and if it is on the right side, then we will be naming this as a D-glucose, and if this is in left side, then we will be naming as
L-glucose.
L-glucose. That's all. And
this amino acid will there is no symmetry element, and if we have the mirror image is
asymmetric center also. Yeah. Carbon attached to 4 different groups.
Okay, lactic acid. 4 different groups, and the mirror image will looks like the opposite isomer.
So we can name optical isomers as enantiomers.
Okay.
These optical isomers are always having a non-superimposable mirror image.
So definition is important, okay?
Yeah, optical isomers or enantiomers that are non-superimposable mirror images to each other
are called as enantiomers. Those isomers which possess non-superimposable mirror images, and these are optically active. So, and they are called as enantiomers. The only difference in those two structures will be in the arrangement.
Spatial arrangement. These notations we have already studied. So, no need to provide representation. We are not showing again. Okay.
And they cannot be interconverted, means under ordinary conditions. If we want to convert the D-glucose into L-glucose, that is not possible under normal conditions or ambient conditions.
Then bond breaking is needed basically. Then only it can go to D-glucose to L-glucose, isn't it, madam?
Yeah.
So they will not be interconverted.
And interestingly, the properties, the chemical properties,
melting point, density, reactivity, that will be almost similar.
Similar for the enantiomers. And the only difference is that they will rotate the plane polarized light to opposite direction. The magnitude will be the same. If one isomer rotates plus 18, the mirror image will be rotating to minus 18.
That,
so the magnitude is same.
Magnitude they will not understand that.
Yeah, that value will be the extent of rotation will be same, and but the only to the opposite way.
Extent of rotation, what we mean here is this theta value.
Yeah, theta value.
So these are we have already discussed. These are the different enantiomers.
Next is diastereomers. These are also isomers.
Diastereomers are isomers. Those are stereoisomers. Those are not mirror images to each other. That means they will be, if an enantiomer is having more than one asymmetric carbon, then only these diastereomers can exist. And these diastereomers are, think once again time, diastereoisomers that are not mirror images to each other are called as diastereomers, and they have a entirely different chemical and physical properties like melting point, solubility, density, and reactivity towards acids and bases that will be different only. And they may or may not be optically active. Let us see some example, then we will understand.
Yeah.
There is this is D-glucose and D-galactose. These are diastereomers to each other. Actually, for glucose, there are three. One D-mannose also is there that we are not speaking now. So D-glucose and D-galactose, those are diastereomers to each other.
This glucose and galactose are not mirror images. You can just look at into the first carbon, not the second carbon. That is HOH. Here, the mirror. If we are taking the mirror image in the galactose, that OH should come on the first one. This asymmetric first. Yeah. Here, if it is a mirror image, that OH should come on the left side of galactose.
Simply by seeing
they are not mirror images.
Simply by seeing itself, it is very clear these are not mirror images to each other, because the first carbon that is located both cases, it is the right only, and second carbon both are located to left only, and where in case of third carbon there is a difference, and the fourth carbon also there is a difference. So in case of glucose, this diastereomer of glucose is galactose and D-mannose.
Simply want to say that they are not mirror images, but the structure is the same. Structure is the same means the just orientation is different, but we can't get mirror images of these two structures. We can't get the relation, that mirror image relationship between two these isomers, to the structures.
Yeah, let us come to the case of tartaric acid. In case of tartaric acid, there is two asymmetric center presented here, isn't it, madam? So there is one first carbon, second carbon, third carbon, fourth carbon. Four carbon atoms are there, where third and fourth second and third carbon, there is asymmetric center is there. Yes. If we are considering the mirror image, then tartaric acid can exhibit its enantiomers also. These two are
one and two structures.
One and two are enantiomers or optical isomers to each other.
They are exactly the mirror images, but non-superimposable mirror image.
Exactly, they are non-superimposable mirror images, and this is D form and its L form is this one, where it can show one more configuration where all OH are coming on the same side. If both the OHs are coming on the same side, this molecule can exhibit a plane of symmetry.
Yes.
If any symmetry, as we already told, if any symmetry is present in a molecule, then that will not show any optical activity, or that will not be able to rotate the plane polarized light.
Yes.
That is very this is a classical example of such compound. If we are considering the iso with the optical isomer, or if you are considering the mirror image of this mesotartaric acid, this tartaric acid that OH is coming on the same side, we are naming that as mesotartaric acid, and that mesotartaric acid mirror image, if you are considering, means that third and fourth images are all same only, because if we rotate the molecule into 180 degree, what will happen? The molecule will exactly come, this same molecule it will come. That means third and fourth molecules exist as, that is, both the molecules are same only. If you rotate into 180 degree, then it will be same only. If you are rotating the D-tartaric acid, first we can just see, this is now, it is in 0 degree only. So if you are rotating to 180 degree, it will exist as D-tartaric acid only. Okay. Now also this is mirror images to each other. But in this case, what I told is third and fourth compound both are same only. If you rotate the fourth compound 180 degree, what will happen? That will form the third compound. Okay. If you rotate into 180 degree. Okay. They are. Now this is become third compound. Their fourth compound itself existence is not there. So both are same compounds only. But in case of 1 and 2, they are not, if you are rotating 180 degree also, they have their own identity. Now it is still it is L-tartaric acid only, and both are existing. And another thing, if we consider, if a molecule is having a plane of symmetry like this, there are two asymmetric center here. So here this form, it will rotate the light to the right direction, and to same extent this will rotate the light into left direction.
So that will
cancel each other. So if we see the one chiral center is rotating light here, then again it will be rotating back to the other carbon, will be other asymmetric center will be rotating back to here, and ultimately the viewer will see the plane polarized light is not having any change, and he will say that this molecule is optically inactive.
So that is
the aggregate total optical activity of the molecule, it will not be
zero. It will be zero. Yes. So the diastereomers are those isomers which cannot form any mirror images with each other, or we can't get
stereoisomers that are non-mirror images that are named as diastereomers.
So they have different chemical and physical properties, and they can sometimes they will be optically active.
Sometimes they may or may not be optically active also.
Yeah.
That is what they are optically active in case of this galactose, where in case of tartaric acid we have seen that they are not optically active.
So this is all about the chirality, optical activity. So we have learned several new terms, that is chirality, enantiomerism, enantiomers, diastereomers.
And their examples also.
Yeah, that chirality means if we have 4 different groups attached to the carbon as different, they can be called as chiral, or this chirality arises as another thing is that they will have no symmetry element in that, and those molecules are optically active, and the isomers which are mirror images to each other, or and thus mirror images are non-superimposable, then that is called as enantiomers, and those isomers which do not form any mirror image relationship is called as diastereomers. Okay.
Stereoisomers, those are not mirror images to each other, are called diastereomers.
Okay, that's all for this session. Thank you.
Thank you.